So, good evening to all of you. So, we have started our discussion on fluid kinematics, and we will continue our discussion on that same. So, in the last class, we have discussed about the streamline, not on the stream tube. The stream tube basically, when you combine many streamlines together, they will make a tube-like structure, and that is nothing but stream tube. A bundle, just like a cable wire, when you open the cable wire, a very thin cable wire, when you open it, you will find in that what you will find in that so many it consists of so many thin wires. So just like a one streamline what we have, when you combine multiple streamlines you can form a tube, and that tube is called the stream tube, right? Just much like a communication cable wire. It happens, right? In reality we do have stream tube kind of structure, right? Whenever the flow is happening in a, let's say, nozzle, so it will be like this only. It consists of multiple what we call, you know uh, streamlines. In a 3D figure you try to visualize, not in a 2D figure. In a 3D figure it will be there, complete uh, picture of streamlines. And when you just make the tube, while combining all this streamline, you will find one stream tube structure. Not that much important, but to have the clarity we have to note down. Note on the next path line. So path line is nothing but the actual path which is being traveled by individual fluid particle over some time period. Path line is the actual path which is being traveled by individual fluid particle over some time period. We call that to be a path line. Just like a fluid particles is there which is being traveling, right? So whatever the history of the particle is there, that can be measured, that can be we can see through this path line. So what we can write? It is based on the Lagrangian approach. It is based on Lagrangian approach. That is the first thing. Second thing, a path line can intersect itself. Whatever the path line is there, that they can single particle is there, you know, it can basically cross itself, right? Path line is for single fluid particle, for single fluid particle. All of you have noted down. So the history start from time t equal to 0 to time t equal to capital T. Once it is done, let me know. So apart from this streamline and path line, we do have one more line, that is a streak line, and that is a very important. Done. Please note down, and please join the class on time, guys, especially in my classes. I need to tell a lot of things, so definitely I need some more than 2 hours always. So, done. Now, note on the streak line. A streak line is a locus of fluid particles. A streak line is a locus of fluid particles. A streak line is a locus of a fluid particles that have passed sequentially through a prescribed point in the flow field. Now, do not make this diagram. I will explain you this diagram after some time. Let me explain through one another example. So you first note down from here to here only the definition of streak line. It is a locus of fluid particles at an instant which have crossed through the same point. Now, so let me explain that. Then I will get back to the definition as well as what you call the figure which is being given in the slide. So let me just say the nozzle is there, or maybe some dye injector is there, which injecting some kind of bubbles or fluid particles you can consider. Let's say the bubble sequence is one, 2, 3, 4. 1, 2, 3, 4. So four particle I have considered, right? Hypothetically, you have to imagine, as there are infinite number of particles are there, but for the sake of simplicity, I am considering only four particles. Now, in these four particles, what I have to do, the very first thing that we have to think about the path line. Let's say the path line of the particle number one is something like this. Path line of first particle which is being injected. It is injecting, and it is traveling. Let's say it is traveling like this. This is the path line of first particle. The after injecting from the point P, let's say the particle one is traveling along this line. That is a path line one. After some point of time, point particle number two will also be injected through the point P, and let's say it has traveled a distance like this. This is the path line of second particle. Path line of third particle. Path line of third particle. Let's say something like this. Path line of the third particle. Let's say something like this, and the path line for the fourth particle is like this. Because we never know, right? It is a unsteady flow. I'm talking about unsteady flow, and in unsteady flow, you know, it is not necessary that every fluid particle will follow the. Hello, hello. I'm audible. All of you can hear me. Is that any breaking is there in the voice? Can you please check, Abhishek? So the path line of the fourth particle, we will be having something like this. As it is unsteady flow, so we cannot guarantee that every particle will follow the same path. They can follow some other path. Every fluid particle can travel with some different velocity, right? Now, and velocity is having both magnitude as well as directions. Now you understand what is the meaning of path line. Let's say at time t equal to capital T second, I want to locate my particle number 1, 2, 3, 4. Where is my particle 1? Let's say at time t equal to t, starting from 0 second, my particle 1 is here, somewhere here. Particle 1. Let's say my particle number 2 is here. At time t equal to t only, capital T, and my particle 3 is here, and my particle 4 is here. So I have just pinpointed the basically location of a particle at time, all the particle at time t equal to capital T second. What I will do, I will join all this locus of points through one line, something like this. And I will connect this line from the starting point. So this is my streak line at small t equal to capital T second. Let's say I want to calculate, I want to see my streak line at time t equal to 2t second. So let's say the particle number 1 is here, particle 2 is here, particle 3 is here, particle 4 is here. So what I will do, I will join this locus of all the particles through one line, but I will not left it by while joining all the points simply like that. I will connect this basically point to the starting point, because everything is injected through a starting point. So I will just connect this to the starting point like this. So this is my streak line at small t equal to capital 2t second. Make a note of it. So I hope that the streak line is clear. So what is the meaning of a streak line? A streak line basically telling you that in a very short term, I would say that it is related to the identification of It is related to identification of identification of location of location of different fluid particles. Different fluid particles. You can identify, okay, just by seeing the streak line, particle 1 is here, particle 2 is here, particle 3 is here, particle 2 is here, particle 1 is here, right? So it is also one kind of what we can say uh, Eulerian approach. Getting my point? Yes or no? Can we say like that? It is for the multiple fluid particles, right? This line is also for multiple fluid particles, not for the single particles, right? This is a very, very important. Make a note of it. Once it is done, let me know. Make a note of it. Now, all of you have noted down. Can I move back to the previous slide to explain that figure? Yes, correct. At a particular instant, it's a more like a Eulerian based approach because it is for the multiple fluid particles, right? Not for the single particles. Now you try understanding this particular figure, how they have drawn this figure. An object is there. On that object, the dye is being injected from here, and it is being injected from like this. So what you have to understand here, the particle one may follow this path, particle two may follow something like this path, and particle three may follow this path. Individual path lines. I'm drawing individual path line. Particle four, they may follow this particular path, fifth and sixth and seventh, right? But it's a coincidence situation that every fluid particle, let's say I want to draw time t equal to capital T second, I want to locate my streak line. So particle 1 is here, particle 2 is here, particle 3 is here, particle 4 is here, particle 5 is here, particle 6 is here, particle 7, particle 8 is here. So when you just join the locus of all the particles through one line from the starting point, you will get one line. That line is called streak line at time t equal to capital T second, right? So make a note of it. So these are the path line for first particle, path line for second particle, path line for third particle, path line for fourth particle, something like this. No, see, view whatever the phenomena is happening, that is a time-based phenomena. You are correct up to some extent. See, the path line is telling you the individual time history of a single particle. You are basically making the video of a particle. That is a true sense of path line. But what you are doing actually at a particular instant, let's say at any, you have this stopwatch, you are stopping, and you will see where are all the particles are there, right? And you will take the picture of that, right? That is snapshot of that instant or moment. You will call that line to be a streak line. But a streak line, when you see that containing number of fluid particles, right? When you start studying the behavior of a streak line, what you will find, whether you will study like a Euclidean based approach or Lagrangian based approach, because Lagrangian clearly mentioned that won't bother about all the fluid particles. I will bother only about single fluid particles. Tell me, guys. If every fluid particle will follow the same path line, then what you can have? Then you can have a streak line that will become a path line, and that will be Lagrangian based approach you can study. That is only for the what you call the study flow. Now, once it is done, let me know. I will explain what is the meaning of study flow. Path line is a time history of individual particle. If you want to have analysis of, let's say, the fluid layer, fluid particle is there. You know, let's say you have the ED. Suppose you have the diverging flow. We have the flow suppression which is being initiated from any of the diffuser wall. So what will happen? This flow suppression, the particle is there. This in this region we want to analyze what is the kinetic energy of that particle, what is the energy, total energy of that particle, right? Because that is like a dead body, right? We want to analyze, we want to do the post-mortem of that dead body. What we have to do, we have to see complete picture of that body from inside, right? So for that, we will be required what is the time history of that fluid particle from starting, from where to where it has traveled, what was its time history and all, right? So in that sense, we will be very much interested to know about that. But that is a very microfluidics level of thinking about the path line of single fluid particle. That is of totally useless as far as the fluid mechanics is being concerned, right? Because here that single particle, forget about single particle, billions of particle is there, right? You will not be able to identify which is a dead body, which is not the thing, right? Just like happened in the COVID time in a particular area, lot many bodies are there, right? So you will not be able to identify which is the body if there are multiple bodies are there. So here, what we have, billions of particles are there, very difficult to identify. Still, we are studying just like a path line means just like a steel ball which is being traveling, right? And we can identify and we can see, okay, these are the path line, these are the motion which is being traveled by individual particles. Did you remember? Now, so when you, if you have any further confusions, yeah, correct. Smoke which is there, which is from the cigarettes, that is of the streak lines. So when you study MIT, if you need that, I will send in the WhatsApp group. One MIT PDF is there based on they have done the study on streak line. They have mentioned that it is strictly an Eulerian concept. Getting my point? Now, can I move to the next one? Now, so note down further about this concept of, yeah. So for a study flow, till now what we have observed, few points regarding the study flow. Let's say we have the study flow and we have the unstudy flow. We have unstudy flow. In a study flow, my different, let's say we have the streamline, something like this. And what we have, suppose, for example, at the moment I am drawing, these are the pattern of streamline. What is this? Patterns of streamline. Patterns of streamline. Suppose the fluid particle, let's say one, two, three, four. For a given instead of time, if I draw the tangent over here, I will be getting one velocity vector v1. If I draw here, I will be getting v2. If I draw here, I will be getting what, v3. Now at time t equal to t1, let's say the particle velocity is what? Particle velocity is in the same directions. At time t equal to t2, the particle velocity is what? Once again the same, because it is a steady flow. So dou u by dou t will be 0. The velocity will not change with respect to time. When the velocity will not change with respect to time, now tell me whether any pattern of streamline will change. V1 fixed in both magnitude and direction, right? So what we can have, the pattern of the streamline will not change. Pattern of streamline will not change. The moment we have the v1 velocity, for example, let's say here at time t equal to t1, but at time t equal to t2, the particle is changing its direction as it is an unsteady flow. Either I change the magnitude or I will change the directions. I can have the different streamline, something like this. It has, now it is being traveling like this. So if I draw the tangent, I will be getting v1 dash something like this, because the pattern of the streamline has been changed because of unsteady flow. So if I draw the tangent, because velocity is like this, if I draw the tangent, I will be getting a streamline pattern something like this, right? Now this is the streamline we are getting at time t equal to small t2 second, right? So what is happening over here? At a point A, velocity A, that is the velocity of the particle at A, is v1 at time t equal to t1 second. But velocity of the particle A is v2 or v1 dash at time t equal to t2 second, right? So pattern of the streamline will be changed. Pattern of a streamline will change. So make a note of it. Now, what is the consequences of that? What are the consequences of that? Now you have to imagine a particle. Now you have to imagine a particle which is being traveling on a first streamline, right? When the particle is being traveling on this streamline, now tell me they will not change their directions or they will not change their magnitude, right? So what will happen? They will remain on the same streamline, because we know that the particle, my dear friend, the particle, all the particle number 1, particle number 2, particle number 3, particle number 4, particle number 5, particle number 6, they will not change their directions. The pattern of the streamline will not change. So it is something like they cannot move like this, they cannot move like this, still they cannot move like this, they cannot move like this. So they will remain on the same streamline. So what we can say for a steady flow, path line, streamline, and even you draw the locus of all the fluid particles from a starting point, you will be getting same line, which is being joining from the starting point, that is a streak line. So for a steady flow, what we can write? For steady flow, path line will be equal to streamline will be equal to streak line. Right. Now, unsteady flow, my dear friend, what can have? Suppose a number of particles are there which is being traveling on this first streamline, right? So what can happen? Some particles are traveling like this, and the moment unsteady flow is there, so some particle may travel like this, some particle may travel like this, right? So what we can have? We cannot have the same streamline and we cannot have the same path line for our individual particle. Even when you join the line from the starting point, we may have the pattern of streak line, something like this. So all together we can say path line of a particle and streamline and streak line all are different. Just like what we have discussed earlier, individual particle may travel individual path line. Why it will travel? Suppose a particle 1 is there, he is traveling like this. The particle 2 is there, particle 2 will travel like this. Particle 3 is there, particle 3 will travel like this. Particle 3 will travel like this. So they will not have a fixed pattern of a streamline. Getting my point? They may travel with a different what path line, and what we can have different streamlines will be there and different streak line will be there. So for unsteady flow, we cannot say the path line that is equal to streamline that is equal to streak line. Getting my point? Once it is done, let me know. So for a steady flow, all the three lines will have to be same. All the particles would follow the same path in steady flow. It does not matter, it will be straight. No. Streamline will always be a curvature line. It will have a curvature. Or maybe it can have a straight line when it is flowing through a constant diameter pipe. Getting my point? Suppose particle is traveling on a fixed straight line. The What about the streamline? Streamline will also be like this. Same. Both will be same. Tangent of velocity as well as streamline will be same. There will not be any curvature. Why there is a curvature? Because particle velocity or direction is being changing in a circular flow motion and all. Now, so note on the few points regarding the path line, streamline, and streak line. If the flow is unsteady, the surrounding fluid velocity field will change. If the flow is unsteady, as we have seen, the surrounding fluid velocity field will changes. Why it will change? Either magnitude or directions. It will change, and we cannot expect the resulting streak line to resemble or to look like a streamline or a path line at any given instant of time. However, if the flow is steady, all the three lines, whatever the lines we have studied, streamline, path line, and streak line will be same. In short, A streamline represents an instantaneous flow pattern at any given instant of time. Right. A streak line is an instantaneous snapshot of a particular time integrated flow pattern. And a path line is a time exposed flow path of an individual particle over some time period. Tell me, guys, one question has been asked. From aeroplane, if I throw the ball, what will be throw the ball in the basically what? Air, the ball will come down. Then what about the pattern of streamline? For example, airplane is there, whatever the airplane is there, which is being traveling, and the ball is being thrown out. It will travel like this. So what about the streamline? Air drag will be there. Air drag will be there, but that air drag, whatever the drag is there, what is the drag force by the air? What about the drag force by the air? That will be small. That will not be that much high because according to Stokes law, you will be having some air drag. What is that? 3 pi mu, something like this. If we just assume this is the ball of diameter d, so they will offer some kind of drag force, right? And some weight of the body will also be acting. No, just a ball is being thrown from an aeroplane window. As the viscosity of the air is very small, you know, so the drag force which is being there, which is being imposed by the air will also be very, very small, right? So there is no option. It is just being asked in one of the interview. You just think and let me know the answer. That is a very good question. Now, all of you have noted down this particular point. Is it done? No, we have to draw the streamline. Now, try to think of this particular question which is being asked in aerospace 2014. In A 2014 paper, they have asked one question. To observe the unsteady separated flow, in a diverging channel, the bubbles are injected, at each 10 millisecond interval at a point A. The bubbles act as a tracer particle and follow the flow faithfully. The curved line AB, whatever the curved line is there, AB will be called as what? So when you take the curved path from A to B, the individual particle may have traveled like this. Particle 1 is here, you know, particle 2 is here, particle 3 might be here. But the blue color which I have drawn, that is being connecting all the fluid particles at some time t equal to t second. That is my streak line. Because this line containing number of fluid particle 1, 2, 3, 4, 5, and number of fluid particle means what? When we have the multiple fluid particles, which line is generally resembling, which will give you the snapshot of all the for all the position of a fluid particles, only a streak line. Now some of you might be thinking why it cannot have a streamline. Tell me this. Because when you consider streamline, what do we have? That is also for the multiple fluid particles, right? Correct, correct. Because streamline, when you draw, at any point when you draw the tangent, it will give you the direction of velocity vector. It has nothing to do with the identification of particles at a given instant of time, right? It is of no use of that. We cannot tell by using the pattern of the streamline, right? With the help of pattern of a streamline, it is only showing only one pattern, right? It is only showing the one pattern, and of course that cannot have, because it is unsteady flow, so definitely it is not the streamline. So it can have only the streak line. Now tell me, if it is a steady flow, then we might have a option, that is all the streamline, streak line, and the path line will same. But separated flow cannot have the condition of steady flow. That is highly unsteady flow, separated flow. Right. Done. Is it done? Now tell me the timeline. The next concept, timeline. As the name itself is suggesting that over a given period of time, or basically at a given instant of time, uh, whatever the the set of adjacent fluid particles, right? It is telling you the set of adjacent fluid particles. Let me tell you. Suppose this is the fluid particle or some velocity flow field. Note down the first of all definition. These are the lines. Timeline are the lines formed by, it is a line. Don't think that it is a history telling, just like a, path line, not like that. Timeline basically are the path line, are the lines formed by set of fluid particles, formed by set of fluid particles that were marked at a previous instant in time, at a previous instant of time. Now suppose we have the fluid particles, assume the fluid particle which is being injected like this, for example. Means I'm just analyzing which type of flow field it is there with the help of timeline. For example, the fluid particle 1 is here, particle 2 is here, particle 3 is here, particle 4 is here, and just connect this all the four particle by some line. For example, let me just consider this through a line, something like this, just like a thread. Assume it like thread. All the fluid particles are basically connected to this thread, right? At time t equal to 0, for example, now the flow is happening. These are the fluid particles that were there instantaneously at some given point of starting point of time. They will be there. But now let's say the flow is happening with some free stream velocity. Now the particle which is being marked, now they have been displaced from their position, something like this. When they have been displaced, so what will be my thread? Thread will look like this. The thread will look something like this. Further, what will happen at some given instant of time? My particle will be something like this. And if I join through this thread, I will be getting like this. So what we are observing is that uh, it is which kind of flow field, because you can only see that there is some deformations are happening, right? Fluid particle initially were straight, but now they are deforming, right? It is something like this. Something is there that is rotating the fluid particle. What is that? Rotational flow field. It is a rotational flow field, right? So it is a rotational flow field. That's why the thread is basically bending or taking the curve shape. But for example, we have the fluid particles, and that fluid particles we have the thread, something like this, that were initially straight, and they were straight even after flow is happening. They will be straight all the time. Then what we can say at t equal to 0 hours, 1 hours, 2 hours, then what we can say, this is nothing but non-viscous flow field. Non-viscous flow field. And what about the first field? You are saying that rotational or viscous flow field is there, right? Rotational means force vortex, and irrotational, what we call that to be what? Free vortex. Getting my point? Vortex flow is a two types. One will be one will be called as basically one will be called as force vortex. Second will be called as free vortex. You can say that uniform flow is there about the non-viscous flow, because whenever the non-viscous flow is there, the velocity profile remains unchanged. It will not either move in radial direction or in the axial directions. It will remain same, just like a free stream velocity conditions. So timelines are the lines, these yellow lines, which are formed by the set of fluid particles that were marked at a previous instant of time. So these particles are there that were marked at some given time point of time, and we will see how these particles are changing their positions. See that over the given period of time. I will be connecting through this all the particles through one line, right? That is my timeline. So that is the fourth line. So there is a no connection of this with the streak line or what we call path line. It is a different, because these lines I'm joining not from the starting point. Let's say they have been injected from here. I'm not joining like this. Don't think that it is connecting all the fluid particles. So this is a streak line. No, I'm just joining through instant of time. That's it. I have just and marked. I have just marked the points. Okay, these are the particles at time t equal to 1, 2, 3, 4. Means at given time 1 second, adjacent fluid particles are at this location. I will be joining that through a line. So I'm not joining through a starting point from where they have been injected. Can I move to the next one? Is it done? Yes. If you want to do the experiment, somebody will be asking you how you will check whether the flow field has been viscous flow or non-viscous flow. So what you will say, sir, boundary layer formation is there, but boundary layer formation is there, you can say by that, but boundary layer is a very thin region, very very thin region as compared to the fluid domain, whatever the fluid domain is there. So we cannot actually identify through that. So definitely we have to follow some timeline method to identify whether the flow field has a rotational flow field or irrotational flow field. Done. Can I move to the next? All of you have noted down. Can I move to the next one? Now, note on the next concept. That is nothing but now trying to answer this question. Consider the following statement regarding the streamline. It is a continuous line such that tangent to it streamline at any point, it shows the velocity vector at that point. There is a no flow across this streamline, and these are the equation of a streamline. That is correct. In unsteady flow, the path of the particle is same as streamline. That is not correct. So 1, 2, 3 is correct. So D will be correct. Right. So make a note of it. There is a no flow across the streamline. Suppose two streamlines are there, and particle one is here, which is being traveling, right? So this particle cannot flow across the streamline like this because the net velocity is in the direction of something like this along the tangent directions. All the net velocity, right? Some particles are having u, some particles are having v. The net velocity is like this, so they cannot travel perpendicular as there is a no component of velocity. Normal component is zero, right? Now once it is done, let me know. Not only types of motion or deformation of a fluid elements. Just like a solid body, they can also translate, they can also rotate, they can have the shear deformations, and they can have the linear deformations. As you can see, this is translation. It is being mentioned in the figure. It is being given translation. B is a rotation. C is nothing but linear strain rate, and this is nothing but shear strain rate. This is the shear strain, and the term we use notation wise rate, because in fluid mechanics rate of deformation is important rather than deformations. So in the SOM you might have studied the strain, right? change in dimension by original dimensions. But you might be thinking, sir, here what is the particle dimensions? How we can analyze the fluid particles dimensions? So let's see one derivations, and then in a very similar fashion we can write for other parameters like other motion, that is rotation, linear strain, or shear strain, and translations. Let's see for a linear strain or linear deformation of a fluid elements. Done. Can I move to the next? See, here we try understanding. There is nothing to write as of now. Now, linear deformation rate. Just like what you have done, is study about the solid body. Let's say we have this solid body. When I just apply the load to this solid body, there will be some deformations will happen. There will be some deformations which will happen. Delta L. And this deformations, my dear friend, we will be calling PL divided by A. Right. Similarly, in the fluid also there will be some deformations, right? Something like this. Suppose there is a flow field and there is a fluid particles, and on any fluid particle layer I'm considering the layer, suppose like this is my layer of the fluid particle A, B, and on that I'm applying some kind of shear force to move that fluid. AB is a fluid element, or we can write fluid element, for example, fluid element. So what we can write, my dear friend, what we can write, the particle, let's say A and B is there, from here to here, particle A and B, which is being connected, right? Means you just assume a thread which is being connecting AB as a fluid particles. Now, in a given instant of time, let's say they have the initial gap of dx, and the particle A is traveling with u, and particle B is traveling u plus dou u by dou x into dx. For example, right? They are moving with some difference of velocity, then only the deformation will be there. Agree with me or not? If they are moving with the same velocity, any deformation will be there. Tell me. Let's say particle A and B, they are traveling with the same velocity, no deformations will be there, right? But they will travel with some different velocity. Suppose particle A and particle B, particle A is traveling with u and particle B is traveling with 2u. There will be some deformations like this. In the fluid particles, there will be some deformation with respect to time, right? Now, let's say after dt time interval, the particle A is has been there here. Where? Here. A dash B dash. This is my particle which is being stretched, right? You have to assume that it has been stretched. So particle A from here to here, how much of distance it has traveled in a dt amount of time? In dt time, the particle A will travel u into dt. And what about particle B? Particle B would have traveled from here to here u plus dou u by dou x into dx into dt, because we know that what is the velocity, distance by time, so distance will be velocity into time. So through that segment we are getting this one. Now what is the strain rate, right? First of all, note down the strain. What is the linear strain in x direction, as we are focusing our attention in the x directions? So what is the strain in x direction? Tell me, guys. Change in length by original length. Can we write like this in a simple definition? You assume AB like a solid body, and now the length has been changed, that is a dash b dash, you know. So change in length by original length, can we write like this? Yes, we can write. Now tell me a b dash, what we can write? Can we write a b dash from here to here? A b dash, can we write? That is equal to a dash plus a dash b dash. Check it out. Can we write like this? No problem at all. No problem at all. Now whatever the a dash is there, what we can write? That can also be written as, sorry, that can also be written as, you understand, that can also be written as ab plus bb dash. See, from here to here, how we can write the total length? A dash plus A dash B dash, or AB plus BB dash. In both the sense, we can write like this. Now from here, I need to calculate A dash B dash, A dash B dash minus AB. I can write this to be BB dash minus AA dash. Same thing I'm writing over here. BB dash minus AA dash divided by AB. So my dear friend, what we can write further? BB dash. What is the BB dash? BB dash. What we can write from here to here? How much of distance it has traveled? U plus dou u by dou x into dx into dt minus a dash. A dash is nothing but from here to here. How much of total distance? U dt. U dt divided by u dt. Dt I can take out and I can write over here, and I can write further dou u by dou x, that I can write, because u dt will cancel out, dou u by dou x, and dt will also cancel out, right? What we can write? Dou u by dou x into dx into dt divided by u dt. This will cancel out. We will be getting what? Sorry, here. Oh, just wait. Original length is what? AB. What is the AB we can write? That is not UDT. Sorry, that is not UDT. That is DX. Getting my point? What is the distance? See, I have written A dash B dash minus AA dash. And this can be write BB dash AA dash. And this is AB. AB is what? DX only, right? So I cannot write. This is dx. So this will cancel out. So you will be getting dou u by dou x. And one dt is there that will come to this left side. And this we are calling is strain rate. What is that? Linear strain rate in x directions. Linear strain rate in x direction, that is dou u by dou x. Make a note of it. If anybody has not understood, let me know. In a very similar way, what is the strain rate in the y direction? Dou u by dou y. You can prove very easily when the fluid particles are traveling with some velocity v, right, and the flow is happening like this. No, dou u by dou x, sorry, this has to be dou u by dou x. Done. Just think like AB as a solid body which is being deforming just because of the velocity differences. Because unlike in solid mechanics, here you cannot say the deformation purely based on the force, because force is acting same on particle A, particle B. That is a shear force. Because particle A, let's suppose here we have some fluid plate, which is being moving with some velocity v by the application of force. So this is Fs, and they will offer Fs like here. Once it is done, let me know. Done. Can I move to the next one? Now, so note on the other linear strain rate in y direction. Strain in y direction, dou v by dou y. Strain in z direction, dou omega by dou z. In x direction, dou u by dou x. Where uv omega is a component of velocity v omega in x direction, y direction, and z directions. Done. Now, so as you can see, the linear strain rate is defined as the rate of increase in length per unit time. Per unit length, the rate of increase in length per unit length, right? That is a linear strain rate. In a particular Cartesian system, we can write this way. And if I combine together all the things, then what I will be getting? Volumetric strain rate. Volumetric strain rate, something like this. Because if you just consider a cubical element x, y, z, let's say the volume is what? X, y, z. Then what is dv by dt? X, y, dz by dt plus x dy by dt dv by dt we can write x or dx by dt into y into z plus dy by dt into z by applying the chain rule dz by dt like this. And here what we can write, if I will be dividing with the volume, so what I will be getting x y z x y z x y z. So this yz will cancel out. So what you will be getting? Again from here xz will cancel out and xy will cancel out. So 1 upon v dv by dt, that is nothing but volumetric strain rate, that can be written as dx by x per unit time plus dy by dt by y plus dz by dt dz by what we can write, sorry, just wait. Dz by dt into z. Now tell me what we can further write. Tell me guys. Dx by x, change in length by original length in the x direction. That is a strain in x direction per unit time. That will become together epsilon x dot. Dy by y, that is my epsilon in the y direction per unit time. That will become my strain in the y directions per unit time. And similarly, this will become strain in z directions. So altogether, when you combine, you will be getting volumetric strain rate in Cartesian system. Rate of increase of volume of a fluid element per unit volume is called volumetric strain rate or bulk strain rate. Now, once it is done, let me know. Done. All of it done, guys. Is it done? Note down the Sayre strain rate. Sayre strain rate, very very important. What is the meaning of Sayre strain rate? Whenever the fluid particles, yes, basic elasticity, but per unit time we have to study. Suppose any fluid particles are there, which is being driven by the plate, which is having some velocity. What is going to be happening in that fluid particles? That in the fluid particles, what will happen? The fluid velocity, whatever the particles are there, they will be start deforming. And what is my theta? That is dou v by dou y. Or whatever the fluid particle is there, we can write that is completely dou u by dou y. And for a linear velocity profile, we can write v by h. So what if we are writing over here? This is like some kind of Sayre deformations which has been happened, right? For a Sayre deformation, just note down the definition. What is the meaning of Sayre deformation rate or Sayre strain rate? It is defined as it is defined as just like in the solid mechanics, what we have studied about the Sayre strain. In the same manner, we have to study over here. It is defined as the rate of change of angles between the fluid lines which were initially perpendicular, which were initially which were initially perpendicular to each other at a point. It is defined as the rate of change of angles between the fluid lines. That means, my dear friend, what you are understanding from this definitions. Suppose there is a solid body, right? This is a solid body, right? It is being fixed at one end. Now, what I'm doing, I'm just applying some kind of shear force. What will happen? Shear deformation will happen. There, how we are defining the rate of shear strain, or how we are defining the shear strain? This one. Initially, these two lines A, B, and C, they were perpendicular to each other. 90 degree was the angle. But now, what is my angle? it has been less than that. So what is the definition of strain rate? Shear strain. Tell me guys. 90 minus, this is 90 minus gamma. So what we can write? Change of angle between the two perpendicular lines, or two lines which were initially perpendicular. So line AB and BC, initial angle is 90 degree, final angle is what? 90 minus gamma. So what we can write? Gamma. That is my shear strain. In a very similar fashion, here also in the fluid, you have to consider two elements A and B. For example, suppose here the two lines are there. Let's say A, B, and C. So what will be happening? The angle which is being changed between the two original perpendicular lines, because of the flow, what will happen? The fluid will be start deforming like this, right? So what we can write? This will be B C dash. Now tell me guys, what will be the angles? What will be the angles? How much of deformation is there from here to here? How much of deformations is there between from here to here? Or what is the angle from here to here? How much of, by which angle it has been deformed? What we can write? Let's say here we are calling this to be d alpha by dt. D alpha by dt. So what we can write? Strain rate in x plane and y plane. What we can write? Gamma xy, that is equal to, see guys, I'm not here, I can directly give the proof, but my intention is to tell you whether you should whether you are understanding about the topic or not, whether you are feeling about the topic or not. So now here shear strain rate in xy plane will be what? Change in angle 90 degree. Now what is the final angle between these two lines? So what about the final angles between the two these two lines? Yes, if I just assume my fluid particle which is being traveling like this, just wait. No, see. Here there was a, yeah. What is the mistake which we are doing? The two lines which we have considered, that we have to look at very carefully. This is the line AB, this is the BC, right? When the fluid particle is traveling like this, AB line will deform, right? Getting my point, all of you. AB line will be start deforming like this. Getting my point? So let's say this is my d alpha by dt, and this line will become what? AB line will become A dash B dash. Now tell me, what is the final angle between these two lines? The final angle between these two lines will be 90 minus d alpha by dt, right? So in this case, what we can write? 90 initial angle. What is the final angle between these two lines? 90 minus alpha dot. So what is the strain rate in xy plane? Alpha dot will be my strain rate in xy plane. So this is one of the very, very important thing. Please make a note of it. And how to find alpha dot? How to find the alpha dot? That is the next question. How to find that particular alpha dot? That is a very simple. We have already seen our proof of that in the first chapter particle which is being traveling, and the lower particle which will be travel with some lower velocity. Let's say it has been traveling what we call from here to here. It is being traveling at a distance dy. It is traveling at a distance, let's say du, udt. It has been traveling with the velocity u, and this has been traveling with some velocity u plus dou u by dou y into dy. So this distance will be same udt, but this extra distance which is being traveled by the particle from here to here, or let me just write from here to here, this will be dou u by dou y into dy into dt. So what is my this alpha dot? Alpha dot I can directly, or d alpha angle I can write tan alpha. Alpha is very small. We can write tan alpha is almost equal to d alpha, and that is my this distance, that is dou u by dou y into dy into dt divided by what we can write dy. So this will cancel out. So d alpha by dt will be my dou u by dou y, and that is what we are getting from here also. Right? Now, so this is what you are getting strain rate in x direction. But why it is extra term is there? Extra term is there when you have flow in this direction, when you have flow like this also. So both the lines will be start deforming like this. A dash, and my C will be travel to, sorry, my C will travel to C dash. So here it will deform by alpha dot, here it will deform by beta dot. Alpha dot, we know that dou u by dou y, and beta dot will be dou u by dou x. So together, initial angle will be 90 degree. How we are getting this formula? How we are getting this formula? Let me prove that. We are getting this formula as epsilon xy dot, initial angle 90 degree, final angle is what? Final angle is this one between these two lines. 90 minus alpha dot plus beta dot. Alpha dot plus beta dot. So finally, what is that? Alpha dot plus beta dot. Similarly, for other planes, you please note down the formulas. Now, why half is coming? That is a shear strain rate formula, only for shear strain rate. Remember, that is a this thing will be clear when we discuss in the solid mechanics about the strain matrix, right? As of now, you might be thinking, sir, it should be only alpha dot plus beta dot. That is the formula for angular deformation rate. Of course, both the terms are same. Same. I will be telling you the differences. Just make a note of it. Epsilon xy or gamma xy dot, both are same meaning. It's a very easy to remember. Xy is there, uv will be there, and interchange the y and x. Zx is there, which component will be there? Omega and u will be there. Interchange omega with the x, interchange u with the what? Z. That is a shortcut to remember. Now, once it is done, let me know. See, for a linear deformation, my dear friend, you can have the linear deformation also, right? If I show you a very general picture where we can have the both, right? See, for a linear strain rate, you should have dou u by dou x, right? But in this picture, you know that u is only the function of y. So what is the linear strain rate, especially in this case, dou u by dou x will be 0. Getting my point? You can have the both shear deformation and linear strain rate. Both you can have when u is a function of both x and y. Getting my point? Correct, correct. But that is the average what you are mentioning, average of angular strain. That is the definition of the angular velocity. That's some kind of definition which we give for a rotation. One will be the with the sign convention, like counterclockwise positive, anti-clockwise clockwise negative kind of things. Once it is done, let me know. Now, once it is done, let me know. See, say strain rate. Why half is there? Because when you write the matrix, strain matrix, you will find epsilon xx, and then you will find, my dear friend, epsilon xy, epsilon xz, something like this. This epsilon xy actually, we are writing gamma xy by 2, something like this. That's why for this purpose half is coming. Gamma xy, we know that gamma xy alpha dot plus beta dot. But while writing in a matrix form, it is coming 2. That's why we are writing by 2. But that is true when you write when the matrix has been given in the question, right? But sometime it is the only formula which is being given in the Sinjel and Simbala book, that is with the half. But note down the other formulas. What I want to tell you, note down other formulas. Say when they mention in the problem, say deformation rate. Only say deformation rate. Rotation, see, based on the fluid directions, how the fluid direction is there, in which direction is there, based on that the rotations would be there, right? Say deformation rate, we also call it angular deformation rate. This thing we can write, it is the only deformation rate, that's it. That is not the shear strain rate, right? Shear strain, this term strain is basically taken from the strength of material. That's why to respect that subject in and they have mentioned very clearly to certify some condition, tensorial conditions, I will discuss, I'm not discussing over here. That's why some half is coming, because I just now shown you how half is coming. In the matrix itself is half is there. That's why half is coming over here. But when they mention only deformation, that's it. No strain word has been mentioned. Then directly note down gamma xy dot will be alpha dot plus beta dot, that is dou u by dou y plus dou v by dou x. Right? So make a note of it. Similarly, gamma xz will be, you can write dou u by dou z plus dou omega by dou x. Gamma yz will be, sorry, this can be written as, see, because sometime you follow NPTEL assignment, you will find say deformation rate, sometime you will find say strain rate. So to avoid that confusion, you should please make a note of it. Dou v by dou z plus dou omega by dou y. Once it is done, let me know. Done. On the basis of that, we will try to see some of the problem. Just wait. Yes. So when you see in XC paper in 2014, they asked rate of angular deformation at a location of this one. They have given the velocity field. x square y, v is minus y square x. They have not asked anything about the shear strain rate. Then what will be the answer? Simply we need to find dou u by dou y plus dou v by dou x. Dou u by dou y, what will be there? X square. Dou v by dou x minus y square. So that is nothing but x square minus y square. That will be 2 square minus 1. That is 3 unit. No. Sales strain rate half. That is correct, because that is given in the single and that is being already verified. So no need to worry about that. No. That is being specifically. I shown you the proof, right? There is a no need to put half, because I told you uh, the fluid deformation which is being there, right? Directly from here to here, flow velocity which is being there, and I shown you the proof. Alpha dot. This is beta dot. That's simply the deformation which are happening, right? We are not bothering about. We have not defined like that. Initial angle minus final angle. Initial angle minus final angle. But here in the fluid mechanics, it is dot. Done. Can I move to the next one? All of you have noted down. Make a note of it. Is it done? Now here, just note down one more term is there. Rotations. Note down rotations. We call that to be okay. Note down angular velocity. Angular velocity. It is just kind of a very similar expression is there, just like what we have studied, but with the minus sign. Now, note down. It is defined as average rate of average average rate of rotation of two initially perpendicular lines. Two initially perpendicular lines that intersects at a point that intersect at a particular point. That means two lines are there, A and B, C. they will be start rotating. Let's say for example, now it has been rotated in this direction, it has been rotated in this direction by the amount alpha dot, by the amount beta dot, right? So what is we are writing over here, that clockwise rotation we are assuming that to be negative. So d alpha by dt, that is alpha dot, we are writing minus dou u by dou y. It is not coming just because of the flow directions and all, it is coming via sign convention, right? What is the sign convention? What they have written, average rate of rotation, that means omega xy in xy plane, if I want to see in by which amount they have been rotated. So if I want to find, I will do the half alpha dot plus beta dot divided by 2. But here good point is that we have to consider with the sign. What is that sign? Alpha is what? Negative sign, and beta is what? Positive sign, divided by 2. So what we can write? What we can write? Beta dot, we know that dou v by dou x minus dou u by dou y, and half of that, that is my omega xy. Beta dot, we know that d beta by dt, yeah, clockwise negative, anti-clockwise that is positive, like this. So make a note of it. Similarly, my dear friend, omega, what we can write other thing, omega yz. Omega yz you can write half of, see xy is there, you please write xy at z like this. So xy is there, xy is there. Now whatever the x is there, opposite of that v will be coming, and opposite of y u will be coming. Similarly yz, note down the yz like this, with the y which is there. See, there is a yz, means there is no point of discussing about what u. There will be v, there will be omega, but interchange, right? Please remember this shortcut, you will never forget. Zx will be half of, put z, put x in the same sequence, right? But with the z, which one will be coming? U will be coming. With the x, omega will be coming. That is the formula, and almost exactly the same formula is there, but there is a plus sign in the say restraint rate. For a same element, you can have both rotation as well as angular deformations. Just like in the boundary layer region, you have both rotation as well as shear deformations rate. Both are happening. Tell me in which case the shear deformation will be zero, but you have the rotation. And tell me one more case where you have angular velocity zero, but you have pure shear deformations. That is, you have no rotation, but shear deformations are there. These two cases we have to discuss. Once it is done, let me know. This omega xy we can also write. See, this is the xy plane, right? This is the xy plane. We are rotating about which axis? We are rotating about this perpendicular axis, z axis. Perpendicular axis, z axis. So this is my omega z. Sometimes they can write like this, right? And my dear friend, omega xy means which is the perpendicular plane? Z. This is the perpendicular plane about what? X. So sometimes we used to write total angular velocity vector to be omega x I cap, omega y j cap, omega z k cap. Make a note of it. Very, 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 very important. Is it done? All of you have noted down? Can I move to the next one? Now, try understanding the next particular concept about the vorticity and rotationality. Note down vorticity and rotationality. Vorticity that can be written as delta cross V or curl of V, we say. So, vorticity, my dear friend, we can also write vorticity, we can also write 2 times of angular velocity, or angular velocity can be written as half of delta cross V, half of curl of V, right? Because when you do half of curl of V, you will be getting the same thing. What is the delta cross V? I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, u v omega. So when you write I cap, that is dou v by dou x minus dou v by dou y. When you write dou omega by dou x minus dou u by dou z plus k cap dou u, sorry, you will be writing dou v by dou x minus dou u by dou y. And what you are getting, my different, this is nothing but vorticity. Sometimes we also represent like this. So vorticity about xy and vorticity about xz. This is the vorticity in xy. So when you just take the minus sign here, you will be writing like this. Same expression. See, check it out. Dou u by, where is that? See, check it out. Uh, this one. Dou u by dou z minus dou omega by dou x. When you multiply with the two, you will be getting like this. Always in a matrix, we have to multiply like this. First minus second, plus minus plus. Done. Vorticity is a measure of rotation of a fluid particles. That means, my dear friend, what you can write, if omega is equal to 0 and vorticity is also 0, then it is a irrotational flow field. Irrotational flow field, which is being not rotating. If omega is not equal to 0, vorticity is also not equal to 0, we say this to be rotational flow field. Rotational flow field. Make a note of it. And vorticity vector will be xy, sorry, vorticity about x. I will explain. See, when the fluid element is not been able to rotate, that is a irrotational flow field, right? Just like outside the stream, outside the boundary layer, what you have, my dear friend, where you have the fluid. Suppose this is the flat plate, and you have the fluid particle which is being traveling. You have a very thin region where you have the velocity gradient which is being exist, right? Here we have 0.99 times of u infinity free stream velocity. So what will happen? Here you have the slope almost zero. Dou u by dou y is zero. Dou u by dou y is zero. V cannot be there because that cannot be penetrated, right? This is a one-dimensional flow, so V automatically zero. So dou u by dou x will also be zero. So in this xy plane, right, outside the boundary layer, you calculate vorticity or omega in xy plane or omega about z axis. You just calculate it. What is the formula we have? We have the formula dou v by dou x minus dou u by dou y. This is automatically zero. This is also zero. This is zero. So fluid particle will not be able to rotate. It will be flowing like this only. Here fluid particle will able to rotate. Getting my point? Because we have the dou u by dou y. Is that clear? So here we have irrotational flow field. Here we have rotational flow field. Once it is done, let me know. Is it done? Done. Which one? Which one I need to repeat? Sorry, here there is a no yz. Something is missing. Xy is there. There should be some yz should also be there, right? Dou omega. This is dou omega. Make a correction. This is dou omega. Right. So this is nothing but you have what you not xy. This is you have this is v. So this is nothing but sorry. I have written completely wrong. This has to be corrected because I cap is there, right? So this is dou omega by y, and this has to be z, yz or omega x cap. Make correction. Remaining things are correct. It is same as rotation. There is a no uh, past history. It is just like a see. I told you just like when we discuss the some equations. Whenever in the equation, whenever the terms are coming frequently, frequently terms are coming while writing the equation 2 omega, right? Always it is coming together. This 2 omega term is coming always all the time. So instead of telling 2 omega separately, they used to introduce one word called vorticity vector, right? Apart from that, there is a no significance, right? As we discussed about the kinematic viscosity, as well as we have discussed about the dynamic viscosity. There also, what is happening? Mu is equal to mu by rho, right? So upper term is viscous force, bottom term is inertia force. How much of contentment of energy is there? That is rho, right? That is our inertia term, and viscous term is nothing but how much it can diffuse to any layer. So with respect to that, these terms are coming frequently, mu by rho, mu by rho. So they introduce one more term, a relative term, kinematic viscosity. So similarly, in the equation, it was coming 2 omega all the time. So they replaced by one term called what we call vorticity, right? Now, try to solve the numerical. As you can see, inside the boundary layer, what we have? Inside the boundary layer, the fluid particles has been rotating. So that is the rotating or rotational boundary layer region. Outside, it is being straight. It is not rotating, right? Now, try to solve this particular question. The velocity field has been given u as ky, v is given as kx. They are asking what is the vorticity z. That means they are asking vorticity about z axis in xy plane. That means x will be there, y will be there, and minus sign will be there. X is there, so you will not be there, v will be there, and something like this. So what we can write? Dou v by dou x is k, dou u by dou y is once again k. So that is coming as 0. No, what is that? Here, sorry, this is not v. Omega is given, right? U I cap plus v j cap plus omega k cap. So omega they have given as kx. So there is a no dou v by dou x, that is 0. This is 0, big 0. So minus k, that is a is correct. So make a note of it. Once it is done, we can leave for the day. And I will upload the slide. Many problems are there. You please try to go through that. Now, done. Thank you.